So hello, everybody. Good afternoon. Thanks for making it all the way to the end of the day with me. I appreciate that. Thanks, everybody, for coming in. My name is John Handler. I'm a solutions architect with Amazon Web Services, and I specialize on search. So our two search products, Cloud Search and Elasticsearch. So quick scan, because it's kind of, I'd like to know who in the room knows or uses Elasticsearch. Lots of people. That's great. OK, cool. So these two slides are going to make a lot of sense to you all. So who in the room runs any kind of application, database, server, EC2 instance? Go ahead, raise our hands. Yes, everybody does, right? And these services, applications, et cetera, spit out tons of log lines, right? Now, the problem is, if something happens and you have to go look at a log file like this, or heaven forbid, a terabyte of log files like this, what you have is you have trees. You don't have forest. You don't have any kind of view of what's going on. We're going to be working with this data, so let me introduce it just quickly. This is turning on the Wayback Machine. We're going back to July of 1995. This is a public data set of the NASA, I think it's the JPL website. So this is an Apache weblog. Typical weblog here, we have hosts, and we have times, and we have requests, statuses, size of the result that are returned. So we're going to be working with this today. And keep that in mind, and keep in mind all the little parts. What we really want is something that is much more forest, right? Not trees. We want to have a nice dashboard that shows us what's going on so that we can look at it quickly and monitor what's happening, and then even dig into it a little bit to figure out what's going on underneath. So today, I am going to attempt the insane. I'm going to build for you, in 35 minutes, I hope, a full end-to-end chain that will take in Apache weblogs, put them through Amazon Kinesis firehose, and which will deliver them to Elasticsearch service. We'll start up a Kibana dashboard. We'll look at it. We'll build some things. We'll build the dashboard that we showed. And then we'll dig in a little bit and write some queries to query against the data and see what we can figure out. So we're going to start with creating an Elasticsearch service domain. Quick show of hands, anybody used Amazon Elasticsearch service? So some folks, but not everybody. So people are familiar with Elasticsearch, but not necessarily Elasticsearch service. OK. If the gods are good, OK. Hey, cool. So what we have here is, this is our Amazon Elasticsearch service dashboard. And I have a couple of domains running. And I am actually going to create a new domain. Domain is a term that simply means an Elasticsearch cluster wrapped by Amazon services that make it easier to deploy, manage, administer, make highly available, et cetera. We'll see all of that. So we call it a domain, though, as a collective term for what's going on underneath. So to create a domain, first thing I need to do, of course, give it a name. And let's do, what? Handler 302. And then we need to set an Elasticsearch version. As of now, we support Elasticsearch version 2.3 and 1.5. We recommend everybody use 2.3. It's a lot better than 1.5. If you're on 1.5, you should migrate forward to 2.3. So we'll just pick 2.3 and go next. So now we need to configure our Elasticsearch cluster. We have a number of options, and we're going to step through them all and launch a little bit and talk about sort of what's underneath the choices that we're going to make. So the first thing that we're going to hit is the instance count. And I work as a solutions architect. I'll tell you, quite frankly, many, many people are confused about how many instances do I need and what type, right? So just as a quick background, we are going to touch on some of the basics of Elasticsearch. I think everybody mostly knows what Elasticsearch is, seems like, so I won't go into great depth. But Elasticsearch is a search engine. And what does a search engine do? A search engine takes a big pile of stuff and provides you with a means of sending queries against it and pulling out the best stuff for you. Okay? So typical search engine in a traditional setting would be something like e-commerce search, or a website search, or web page search. These are usual search use cases we know about. And the key feature is there's a big pile of stuff. And the stuff is called, each item is called a document. A document is a collection of fields, and a field is simply a named value pair. So going back to our Apache example, I would have a field which would be the host, the requesting host. And the value would be whatever was in the log line. The full log line would be one document. Documents are then taken in. Elasticsearch creates an index out of them. The index has all of the documents within that. You query the index. Indexes are logically broken down into shards. A shard is a logical unit, which is a portion of the index, but it's also a computational unit that gets deployed onto particular nodes in the cluster. So we can see that here. I have, in this case, 2 indexes, green and blue. They each have 3 shards. Every shard has a primary, always. Primary is the first one, right? You can also set replicas. So in this case, we set one replica for redundancy, and that's a usual thing to do. Set a replica for redundancy. Those Elasticsearch will then deploy to the cluster in such a way that the primary and the replica never sit on the same node. This gives, again, redundancy, so that if a node goes out, we retain a copy of the data to be able to continue to work with it. So thinking about how many instances, what we want to do is understand that we're going to be deploying these indexes onto nodes, and the index itself will be stored on the node. So we need to have enough storage to hold what the index is, right? So how do we figure out how much storage we need? Well, the documents come in. They're turned into an index. That's a different data structure. But happily, they're about 1.1 to 1 in empirical practice. So generally speaking, how much source data you have is how much index data you have. And that's a really wiggly kind of, okay, we'll just kind of say it's about that, right? If I have a terabyte of source, I'll have about a terabyte of index. So if we're replicating, we need to store it again. So we double, right? And then we figure out how many instances based on how much storage we need. If I have, for example, a 2 terabyte corpus, we figure, okay, that's about 4 terabytes of index. And we need to store that 4 terabytes. If I have, say, 512 gigabytes per node, I need 8 nodes. Pretty simple. It's an easy place to start. It's not the whole picture by a long stretch, but to get yourself started, that's kind of where you want to go. So let's pop back over here. And so now the other thing to notice, of course, is one instance, you can't deploy a primary and a replica on different nodes, right? So you need 2 to have any kind of redundancy. So we're going to pick 2 because the NASA data is only about 200 megabytes. It doesn't need that much. We now have our instance type, and we support a number of different instances, T2s, M3s, R3s, and I2s. The quick guide to this is to say T2s are great for dev and test, but don't use them for production. M3s are general, well-balanced machines. They work really well, but they only go to 2x large. So pick M3s for most workloads. If you need larger instances because you have heavier queries, you're going to go to the R3s, and we go up to 8x large there. The I2s you would pick because they have the most storage. So they have 1.6 terabytes of instance store. In this case, we just need M3s. So far, we have 2 M3 medium data nodes. OK. We are also able to enable dedicated masters. What are dedicated masters? Whoop, I hit the wrong thing. Hopefully, I did that right. Yay. OK. So in every Elasticsearch cluster, you have a master node. The master node is responsible for knowing all the nodes in the cluster, for pushing around config, and for doing what the cluster needs to do. So the problem is the master is potentially a data node. Now, the data node is furiously reading and writing data. So it can become occupied, and the master function then disappears because there's no CPU to do the master function. So that's bad. The fix is to select particular nodes and to move the master function onto those nodes only. So you pick dedicated master nodes in order to take the master function and make it solely deployed on a set of nodes. This gives the cluster a lot more stability. And the right number of master nodes to pick is 3. And the reason it's the right number is because masters are elected based on quorum. If you have an even number and then the cluster splits, each half can then elect a master. That's not good. Then you have 2 clusters where there was 1. That's terrible. So 3 is the right number. You don't want 1, that's too few. You want an odd number, more than 1, that's 3. Okay, I'm going to have to speed up. So the master nodes do a lot less than the data nodes, so they can be smaller. In this case, we can use the T2s. Don't use the micros, but you can use smalls or mediums. Next feature we have is zone awareness. Zone awareness is a high availability feature. This splits your cluster into 2 separate availability zones and makes primaries and replicas go into different zones. In other words, you split your cluster evenly into 2 zones, except the masters, there are 3 of them. So we're going to go ahead and enable that. We support both instance and EBS store. The instance store, obviously you get the storage based on the instance type. For EBS, again, based on the instance type, we go up to 512 gigabytes. EBS is a fine choice. I have yet to see performance problems with EBS. And I've talked to a lot of customers who use EBS. It seems to be just fine. I don't recommend the magnetic volumes. So choose EBS, choose GP2s, general purpose, SSDs. You should be fine. And for the volume size, in this case, again, 200 megabytes, 10 gigabytes should be plenty. I do have to quickly touch on this. So we have this advanced feature, which is indices field data cache size. This controls how much data is actually cached when you run queries, essentially. It's unbounded by default, which is kind of dangerous. You run a few big queries, and you'll knock your cluster over. So you need to have a number there. And you want to balance between leaving some RAM for the rest of the Elasticsearch to do stuff and making enough caching so that you get the performance benefit. Our recommendation for that is just to set it at 40%. So 40% means 40% of the RAM will be used for caching. OK. So we now set our security, our access policy. So we provide security through IAM. You set a policy that can either be based on a user's identity, and you'll use signed requests, or an IP address, in which case it could be anonymous. We have a couple of templates here. I actually am going to make it open. Not that you should ever do this, but I'm making mine open to the world. And that's it. So we have then a chance to review our information and confirm and create. OK, so handler 302 goes into a loading state. It'll be about 5 to 10 minutes until it actually comes up. And let us quickly recap sort of what we talked about here. So to get started, pick a set of data nodes which is based on the amount of storage you need per node. Then use the GP2 EBS volumes. Use 3 dedicated masters. We do want to use zone awareness. That splits our cluster. That's nice. And set the indices field data cache size to 40. And what we're going to get within the service, we deploy a set of nodes that is your Elasticsearch cluster. So at the core there, we have those nodes are managed nodes that are running Elasticsearch. They also have Kibana on them so that you can run Kibana easily. We have load balancing in front of the cluster. And we publish a DNS entry, which is a single endpoint, where you can use the Elasticsearch REST API to communicate with the cluster. It's all gated by IAM. So IAM provides you with the security model. And then we do monitoring. We do metrics for monitoring to CloudWatch, and then CloudTrail as well for audit purposes. And I won't belabor the benefits, but some of the benefits that we get with the service, number one, easy to use. As you saw, click, 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 I get a domain, and I get a cluster. In addition, I can actually change any of the parameters that I set by making another call to update the cluster configuration. So if I want to go from M3s to R3s, I can make a single API call. The service will then bring in the new nodes, get the data transferred over. We provide, again, that's the scalability. We make it very easy to scale up. We have the zone awareness feature as our highly available feature. we are open source compatible. So this is a guiding principle that we've had really since we started building the service. We wanted to build something that would be a drop-in replacement for an existing Elasticsearch installation. Make it really easy to use. It is compatible with Logstash, and it also, of course, includes Kibana. We then provide security with IAM, so you can secure your domain. In fact, you have your IP-based and your user-based ways of doing that. We also provide fine-grained access control down to the index level, and also for the HTTP method. And then finally, we have a lot of integration with AWS services. So we have Firehose we're going to see in a minute. We're also integrated with CloudWatch Logs. With a few clicks in the console, you can send your data from CloudWatch Logs to Elasticsearch service. OK, so we're going to switch topics now. So we've created our Elasticsearch domain. Now we're going to create our Kinesis Firehose and hook it up to our Elasticsearch domain. So who is already using Firehose or knows about Firehose? Lots of folks, too. That's great. I actually love Firehose. I think Firehose provides a lot of really great features in the context of Elasticsearch service. Just some of the concepts. When you use Firehose, you create a delivery stream. That delivery stream can have has a destination. The destination can be S3, Redshift, or Elasticsearch. Then you put your records in the stream with a REST call. It's just an HTTP put. And Firehose delivers those records directly to the destination. So that's visualized here. So we have our data source sending source records into Firehose. And then those get sent to the destination, in our case, Elasticsearch service. One of the things Firehose does for you is it sends failed records to S3. So Firehose has retries. If records fail, it'll write those off to S3. So you have a record of the things that have failed. Also, it'll just send all of the records to S3. So if you're already sending your logs to S3, actually you can send them through Firehose, send them straight to S3, and also Elasticsearch. So you have a backup of what's going on. And as of now, Firehose sends data straight through. But I'm really happy to announce today that coming real soon, Firehose will allow you to transform the records as they're going through the Firehose stream. So in this case, you'd send in your source records. They go to the delivery stream. You'll write a Lambda function or point it at a Lambda function that exists. That Lambda function will transforms the records, so, and then sends them back to the stream. The stream then sends them through as it normally would. We will have, at launch, we'll have blueprints for syslogs and Apache weblogs, so, and also kind of a couple getting started ones. So when that rolls out, it'll be easy to just push your logs straight into Firehose, and then or Firehose can actually monitor your log files for you, send them straight through to Elasticsearch. Again, for ingest, I think Firehose is great. So number one, serverless and scales infinitely, essentially. The error handling feature is really quite nice. Like, not to have to worry about retrying records. It does the retries for you. Tracking where failed records went so that you can then retry them yourself are both really nice features. And the S3 backup is also a really nice feature, like to be able to send everything and have a record of it. OK, so we're going to create a Firehose stream. Oop. Awesome. Remember to turn off your reminders. OK, so this is the Firehose dashboard. And I'm going to go ahead and create a delivery stream. First thing I do is select a destination. I'm going to send to Elasticsearch service. I have to give it a name. And I like to give it the same name as my domain. That way, when I'm cleaning up later, I can figure out which stream goes with which Elasticsearch domain. OK, so I set Elasticsearch as my destination. So I have to select an Elasticsearch domain, in this case, handler 302. I'm going to set an index pattern here. So Firehose will write to Elasticsearch, and it will create indices based on a time period rotation. Okay? I have to give it the base pattern for the index. In this case, I just use firehose, and I set my rotation period to be an hour, day, week, month. 1 day is the usual choice, and it's good in the 250 gigabyte range. 250, 500 gigabytes, somewhere in there is a fine choice for daily rotation. In this case, Firehose would create Firehose-November 29th, 2016, Firehose-November 30th, 2016, et cetera, right? If you have a lot of data, up above a terabyte or two per day, you can go down to an hourly rotation. And if you have less data than that, you can go to the weekly or monthly rotation. Okay. Within Elasticsearch, we have a concept of a type. I really don't want to stress on this. The type is simply a way for one index to contain multiple schemas. Not really important, but you do have to fill in a value here. So just put log. The retry duration is the amount of time that Firehose will continue to retry records and try to get them into the Elasticsearch domain. 300 seconds is fine, 5 minutes. We have some choices about our backup mode. We can send, again, failed documents only or all documents. We'll stick with failed documents. And then I pick a bucket. I have an existing Firehose failed deliveries bucket. And I can add a prefix to all the records that are sent there. So that way I know what their source was. Okay. So I now have some configuration options. So the really important one here is the buffer size and the buffer duration interval. If you set the buffer size small, then you get the fastest flush through the pipe, presuming you're not already filling it, right? So this will cause Firehose to flush every megabyte or every 60 seconds, whichever comes first. If you're already way past the megabyte, it'll flush whenever you hit a megabyte. So that's great. That gives you the lowest latency. On the other hand, if you're really pushing a lot of data in, you're going to be flushing quite a bit. And the more you flush, the more concurrent connections you have to hold to Elasticsearch. So there's a balance here between bigger buffers, which will give you bigger throughput, and smaller buffers, which give you higher latency. For us, 160 is great. 300 is also great, probably into the same 250 to 500 gigabyte range. Okay, we can compress and encrypt data in S3, which I'm not going to do. And we can enable error logging, going to do that. I have to create an IAM role that will allow Firehose to talk to the Elasticsearch cluster. And I'm going to do that. This will bounce me to the IAM panel. Here, you have a choice to reuse an existing role. Don't do that. The role itself gets a policy document that allows it to write to a domain. If you do that a bunch of times, the policy document overflows and you can't do it. So always create a new role. And I leave the Firehose delivery there. And again, I embed my domain name and my Firehose stream name because then I can clean this guy up too. All right. So I allow that. All right. And I go next. I have a review screen, and I create. OK, cool. Success. So now we have our Elasticsearch service domain. We have our Firehose pointing at it. And now we need to, well, first we actually need to quick look at a couple of the best practices that we covered in that little segment. So in this case, again, there's a buffering balance that you have to work between latency and total throughput. We are going to use index rotation. So for log analytics use cases, we always want to use index rotation. Daily is the usual value. And then just to keep in the back of your head, the default stream limit is 2,000 transactions a second or 5,000 records, 5 megabytes a second. You can get a limit raise on that, and you can go higher, much higher. OK. So now we have kind of the pieces hooked together, but we have to prepare Elasticsearch to be able to parse and read the log lines and get them deployed correctly. So the first thing we want to talk about is the number of shards. We saw in the first diagram, an index is logically decomposed into shards. Well, how many shards should I use for my index? It's another question that is one of these imponderables. There's a very deep and long answer, but again, there's also a simple answer that kind of is good enough in most cases. And that is to look at the number of shards as being the total index size divided by 30 gigabytes. This gives you about 30 gigabytes as a target amount per shard. Just storage-wise, that's about where you want to be. So if I have 300 gigabytes of index, I want 10 shards for that. Okay? And less is more. So it's tempting to say, well, one shard could never be enough. But actually, one shard will take up all the resources of the node that it's on. So it's OK if you have less than 30 gigabytes to stick with a shard. You do want a replica, but we're talking primaries here. And you set the sharding when you create the index, right? So when the index gets created, you set the sharding. You can't change that value later, right? So it's important to more or less get it right. For log use cases where you're rolling forward, new indices can actually have different sharding. But once you set it, it's done. Another thing to keep in mind is the computational nature of shards, in that when you're writing data to a shard, that data is occupying a CPU. When you're reading a query, you actually read from all the shards in the index, right? So when you're putting your sharding together, think about how many CPUs are in your cluster. If you're writing 1,000 documents per second, and you have 3 shards, roughly 300 documents are getting written to every shard, right? So then you have those guys are active. You have to have enough CPUs to maintain the concurrency that's coming in and going out. Okay. The other thing we set at index time is we set the mapping. So Elasticsearch, again, is a search engine. And when we send in our documents with our fields and data, Elasticsearch parses those fields and applies a mapping, a schema, to that data. So in particular, it's important that we apply the right schema, or we're going to get gobbledygook in our graphs. So if I have something like a host that's a dotted string, I don't want to cut that up into individual pieces. And if I try to graph that, I'm going to get individual numbers out of IP addresses. That's not meaningful. So what we need to do is set not analyzed for all text fields. Okay? Also, again, this is something that we do at index creation time. Now, if I'm creating a new index every day because I'm pumping tons of data in there, I don't want to manually go and have to set up my schema and my sharding every single time for the new index, right? There is a feature in Elasticsearch that's called a template. You use a template to set a regular expression or wildcard to match any index, and then the settings and mapping can get applied based on matching that index. Happily, firehose is creating indices with a pattern, right? So we'll be able to set up a template to match what firehose is sending to us. We can also define the number of shards in the template. So let me quick pop over here. And okay. So here is our template. And you can see the first thing it does is it matches firehose star, right? So all of those indices that I create that are firehose November 29th, 2016, all of those will match. And then I have a set of settings. In my settings, I set the number of shards to 1 because it's a small use case. I set the number of replicas to 1 because we always want 1 for redundancies. And then I defined a custom analyzer, which we'll talk about in a second. For our mappings, we then put the type, log, and then we can use another Elasticsearch templating feature, which is called dynamic templates. This matches fields based on a template. And my match there is star, you can see. So what I'm saying is match every field and then apply this mapping. The mapping is not analyzed, so I'm turning off analysis for every field, right? And I have a couple of other things in there which are less important. I can also override the template for particular fields. So in this case, we're going to have a timestamp field, which is going to be a date. That's important for Kibana, so Kibana can visualize things in timelines, right? We also have the request field I'm overriding so that I do parse that up and I get pieces of the request. And I'm using my custom analyzer here with a copy of the request. Actually, sorry, the request is not analyzed. My copy of it is analyzed. So I'll get essentially the path will be decomposed and the first prefix will go and then the prefix plus the first path element plus the next path element. So I'll get a series of tokens which are pieces of the path. We'll use those to get some nice visualizations and data. Okay, so what I need to do is send that over to my Elasticsearch domain. And to do that, I have to see whether I have an endpoint yet. I do. Okay, so here's my domain. It tells me my endpoint. And I can send my template with a put. I use the template API. And I have to give it a name, template1. Doesn't matter what the name is. And then I send in my web logs. Template.text. Okay, so Elasticsearch acknowledges it's got the template. You have to set the template before you send any data, because when you send data, the index gets created. So it's important to send your template first. Okay. So let's have another quick look at the data, and just so we can understand what we are going to be visualizing. At the top there, I have a line of the original Apache log file. And then on the bottom is an Elasticsearch document. This is the format the data has to go into Elasticsearch. You can see we have fields there like status, ident, timestamp, request, auth, host, verb, etc. So all I did is I wrote a little script that parses up the NASA log data a line at a time and generates lines that look like that so that they can go into Firehose. All the while keeping in the back of my mind that we are going to be releasing the Lambda feature for Firehose that's going to make all of this part really easy. Just to give you a quick view of it, this is really all that it does. Opens the file, reads the lines, it parses the line, and then it appends it to a list that I'm maintaining. I can use the Firehose batch put API. I send 500 of these at a time, and that's it. That's all that script does. So if I come back over here, oh, I wasn't supposed to. I was so anxious to upload my template, I did it early. Okay, so we can look quickly. Just again, give you an idea. There's my regular expression that I use to match the line. I do some time conversion, and actually I can time shift to the present, parse the line, flush the records. Here's the put record batch. That's it, right? So I am going to stream name handler 302 and input file NASA access log July 95. Good. And hopefully good. Okay, so we can see we're now actually pushing records into Firehose. It will take it'll take a little while for them to start showing up. And in the meantime, again, just to review a couple of the best practices that we hit. So use a template for settings. That way, every time an index is created, it gets the settings that you want. Set the number of shards based on 30 gigabytes a shard as a target. In the best case, you have one shard per node. One active shard per node also works. And then for analysis use cases, you want to use not analyzed on your text fields. Okay. So again, we are going to do some Kibana analysis of the web logs that are flowing in there now. In order to do that, first of all, we have to, again, jump in the Wayback Machine. So one thing I happen to know about July of 1995 is that there were 2 shuttle missions. So there was one shuttle mission that was flying from late June through July 5th, and there was a launch on July 13th. Okay? So hopefully, as we look at this data and as we dig into it, we should see some changes in traffic and some differences in what people are doing on those dates. Okay? That's what we're hoping to find. The concept, the overarching concept for Elasticsearch aggregations that you have to understand is buckets and metrics. So Elasticsearch enables you to aggregate based on buckets of values. So we have a simple aggregation here, which is a time bucket, right? What I've done is I take all of my documents and I bucket them based on their timestamp. Okay? Then I can compute a metric on that bucket. So in this case, my metric is count. I just count everything that's in each of those buckets. So when I display this graph, what I'm seeing is this is the bucket of each of these time slices, and this is how many things are in them. Everything that you do in Kibana really has this concept of buckets and metrics behind it. I got confused with Kibana for a long time until I understood this. So let us go ahead and pop back over here. So we can see we're up to 200,000 or so records. And on my Elasticsearch control panel, I have here the Kibana link. So I can simply click this, and Kibana will open for me. OK. So the first thing we have to do is tell Kibana, we've configured the index pattern, which was firehose blah, right? We have to tell Kibana what is the index pattern that we're using so that it can find our data, right? So in this case, we're going to choose firehose star. And we know it worked because it found our timestamp. That's good. We need to have our timestamp. If I accept that, then I can see here that Kibana has actually taken the mapping. Elasticsearch has taken the mapping. This is my set of fields. Again, it's the host name, the auth, the ident, the verb, the size, et cetera, right? So these are all the fields that are in my data. So now in Kibana, I have several panels here, which are interesting. The first one is the Discover panel. The Discover panel allows me to look at my data. OK, no results found. So why is that? Well, because we haven't yet cranked up the Wayback Machine, so we have to do that. Because I'm sending data in from 1995, Kibana is looking according to this time range, so the last 15 minutes, right? That does not include 1995. I can change the time range that Kibana is looking at by going in a number of different ways, but here's absolute time. We need to go to 1995. And in fact, I didn't fix the time zone. I just ignored that. So we'll go June 29th to 1995, August 1st. So we'll cover the whole month of July. OK. If I type that right, OK. So we can see already we have data flowing in. That's nice. If we were in more of a real-time context, we would actually want to have that auto-update. So I can turn on this auto-refresh here. And if I do that, I'd say every 30 seconds, we'll start to see the data updating as it comes in. I have a really long time range on here, so the queries are somewhat slow. OK. This is our Discover panel. So we can see data's coming in. Actually, we could dig in a little bit and look here, and we can see some of the examples of the data and the values that we have. But really, we want to get to some visualizations. So this is the visualization tab. There are a number of different visualizations that you can build in Kibana. We have charts, lines, bar charts, pie charts, metrics, all sorts of stuff. We're going to start with a simple metric. And we're going to go, now we can scope this particular metric to a particular search. So that enables us to measure based on something we're searching over, but we're not going to do that right now. What we're going to do here is just create a metric. This is the count of everything. So we have 443,000 documents in there already. Well, that's kind of cool. We can add more metrics, and we can say, OK, well, would be kind of cool to figure out how many different hosts are attaching or sending requests. So I want a unique count of the host field. And I can do that. So we have, in the time period that's covered, we have 31,000 different hosts that have connected. And the last one that we might want to look at is how much data are we generating and sending out. So we can also do that. We can look at our, wait a minute. What did I do here? I need a plus. Here we go. We want the sum of the size. Size is the number of bytes in the response. And I put that one in. And we've sent about, in the time period, about 12 gigabytes. OK, so that's kind of cool. We have some numbers that are interesting. So let's say metrics. And I can save that. And let's build another one. So let's look at, another thing we often want to know is how much data are we sending out over time, right? So let's go ahead and look at a line chart. In this case, we start out, we have a single dot there. That's not very informative. But what we haven't done yet is set up the bucketing. We haven't set up the buckets on the x-axis. So for the x-axis, we want to add a date histogram. Date histogram will bucket into particular times, and it's based on our timestamp field. And let's go ahead and do that. This is a count of events over time, also an interesting graph. But what we really wanted was the sum of the size. So we can put that in. And it looks kind of like the number of requests, obviously. But here we have, again, a graph that shows us our bytes sent over time. So that's a good one to keep, too. Let's do that. This one, bytes over time. OK. Now, also, we might be interested in our result codes. Like, hey, do we have any 500s? Do we have any 400s, 404s? So what we can do is we can have a bar chart. And let's go ahead and do that. Now, again, we want to see this over time, right? So we need buckets for the x-axis. We're going to have, again, a date histogram. And we're going to add a sub-bucket, which is a terms. So what we're going to do here is we're going to first bucket into time slices. Then we're going to bucket into status codes. So we'll see split bars with status codes across time, right? So how we do that is we pick a term over, what do you call that? Surrounding date histogram with a terms aggregation in the middle. And our field here will be status. And we're going to get the top 5. So here what we have is a bar chart that has, here's our 200 responses. Thank goodness they're mostly 200s. We have some redirects, 302s and 304s. We have some 404s, 500s, et cetera. Actually, it would be a little bit more interesting if this graph didn't show the 200s, because we don't so much care if we're looking for errors. So we can use Kibana, because remember, it's a search engine. So I can say not status 200, and we'll scope this chart to be only the error codes, right? So now we have a bar chart, split bar chart with all of our error codes. Let's go ahead and save that. OK. And the last thing we'll look at is we'll look at, well, what were people looking at? Like, what requests were they making? I'm kind of curious about that. So we can pick a pie chart, and we're going to first figure out people. So let's split the slices. Again, it's a terms, so we're looking at the values of fields. And we're going to pick the host field here and get the count. So in this case, we have the top 5 sources for our requests. We have Prodigy, we have Alyssa Prodigy. So again, like the Wayback Machine, right? It's kind of funny. Like, I don't know. I was going to do geo-IP, but then I thought, like, oh, wait, those IPs have long since moved. OK, so these are the people that are making contacts. Now, another thing, again, is to figure out what they are searching for. So what I'm doing is I'm going to sub-bucket these slices into what are the requests that they're making. So I'm going to split slices. And I'm going to, again, go with the terms. And I'm going to go with the field is the request. OK, well, let's do that. And again, we're getting a little long on the timeline that we're doing. I don't know how we're doing. Yeah, 15 minutes left. Okay, so now what we have is from piweb3.prodigy, mostly shuttle missions STS-71, STS-71 patch small.gif. So basically, people were getting the website banner. Well, that kind of makes sense. But interesting that STS-71 is the shuttle that flew from June to July 5th, right? So we probably will see 70, which is the one that went July 13th, but not yet because we don't have that data. So we can see they're getting some logos, a lot of GIFs in there, right? But that's cool, so let's save that guy too. Okay, this is requests. Okay, so now we have a couple of visualizations, and we want to build a dashboard so that we can monitor and see what's going on. So we go over to our dashboard in Kibana, and I'm going to add my visualizations. So I'll start with my error code counts. Oh, I want to start with my big metrics, error code counts, bytes over time, requests. I can add all those guys. And then pretty simply just drag and drop. Ooh, my screen's not big enough. To create some more or less pleasing organization of these things. And that is how we got from the source data to the dashboard. All right? Now I have also, so Kibana is nice. It's nice for monitoring. It's nice to see what's going on. It's nice for the forest level view. But you can also use Elasticsearch query language to pull out more report-oriented data that's not visual, but that does give you more information about what's going on. So I'm going to quickly go through a couple of examples of that. So this here is a Chrome plugin. Its name is Sense. And it does give you some autocomplete, and it gives you a little bit of, makes it a little bit easier to write queries, because Elasticsearch query language, as we'll see, is somewhat convoluted. So I need to set my endpoint here. So I get my endpoint. And I can put that into Sense. OK. So the easiest thing I can do is I can just do a get against the search endpoint. That's pretty simple. And what we get back is the response. We have 1.4 million, I believe, documents in there already. So as you can see, like as we're talking, it's filling in, right? Now we get results in no particular order, and in this case, we have a bunch of stuff that's in our Kibana index. Because all of Kibana is backed by Elasticsearch, everything is saved in there. That's not really that interesting. I don't want that. I can also specify an index in my query URL to scope to particular indices. There's lots of different ways you can do it, or lots of different things here. You can put an actual index itself. You can use a wildcard like I'm doing here. You can use commas. You can spread your queries how you want across your indices. So if I just get in the firehose area search results, then I see here's a bunch of stuff that are, again, my Apache weblog data. Now, there are two kinds of queries that you run in Elasticsearch. There's query, it's called query context. Query context refers to when I'm running a query and I'm computing a score. That's usually signaled by the query in the query DSL. And in this case, this says, in the query context, match against status 404. So here I'm going to get all of my 404s. And I can look in them and I see here's, again, status 404. I have another one here for readme.txt, et cetera. The other kind of query that you write is called a filtered context query. And in a filtered context, no score is computed, and the matches are cached. So filters are actually more performant than queries, right? So if you can write a filter, you should write a filter. And in this case, I've written a filtered query that's just looking for my 200 statuses. Again, I could go through all of this language. The query DSL is deep and a lot to look at. So sorry, this must not be 200. So I have my 304s, et cetera. Well, that's kind of cool. Let's see if we can dig into that a little bit. So let's see where our not 200s occurred in time. So now we have this concept of an aggregation. Again, we talked about aggregations. Aggregations are what back the diagrams in Kibana, the visualizations. With the query DSL, I can again send a query that's a filter that says everything is not a 200, and then I can compute an aggregation, which is doing statistics on those documents. In this case, I'm looking at the status field and looking for counts of them. So not a time range, sorry. So in all of the time that we've looked at, so I have 104,304s, 440,000 302s, and about 8,600 404s. So I may actually want to find, okay, well, what was the request that generated those things? So I can take an aggregation and sub-aggregate. In this case, I have my buckets. So here's 304, and these are the requests that generated the 304s. But what I'm really curious about is the 404s, because those are usually broken links. So I can come down here and say, okay, here's my 404s, and pub winvn readme.txt is kind of our worst offender with 490, and then there's another pub winvn, et cetera. So if I'm running my website, I want to go and look at these, figure out what's broken here, and fix them. I got a bunch more stuff, but I'm kind of out of time. I want to leave a little time for questions. So let's just pop back over to the presentation. So again, for Kibana, fields should be not analyzed. Then we get nice visualizations. Buckets and metrics is the important concept when building the visualizations. And for time series viewing, use a histogram, date histogram on the x-axis. And then you can do whatever you want on the y-axis. So that's where we're going to sort of wrap up. We talked about Elasticsearch service, some of the benefits that you get running Elasticsearch service as opposed to self-managed. And then we set up a Kinesis firehose stream. We set up our Elasticsearch cluster with a template so that as the data came in, it was all mapped correctly and had the correct number of shards. And then you can use Kibana to monitor and to dig in and diagnose what's going on. And if you really want to dig in, you can go with the query DSL. We have a few next steps. You have your cards that were on your seat. There is a quick lab that walks you through. It's a free quick lab, walks you through sending CloudTrail logs to CloudWatch and then to Elasticsearch Service and building Kibana dashboards. That's kind of nice. There is a centralized logging solution that we've published that talks you through how to build. It's a whole CloudFormation template, et cetera, to gather all your logs into Elasticsearch. And then that's a pointer to our detail page. So thank you very much. Really appreciate your attention. Remember to complete your evaluations.